Okay, we're going to look at P-series here. The P-series is of the form, the sum as k goes from 1 to infinity of 1 over k to the p. And let's look at a couple cases. Let's look at our first case when p equals 1. What's that going to give me? I'm going to have the sum as k goes from 1 to infinity of 1 over k to the 1, which is the sum as k goes from 1 to infinity of 1 over k. This has a special name. This, of course, is the harmonic series. And 1 over k is certainly decreasing. 1/2, 1/3, 1/4, 1/5, 1/6. 1 over x is continuous and it's positive, so the integral test holds. So we should at least make that point, right? But again, f of x is 1 over x is continuous on the interval from 1 to infinity. Really 0 to infinity, but we'll say 1 to infinity here. It is decreasing. I'd like to think it's obvious, right? Because 1 over k plus 1, the next one, is always less than the previous one, so it's decreasing. And everything is positive. And so 1 over k is greater than 0. So we have continuous, decreasing, positive. All three things are true. So if the integral converges, the series converges. If the integral diverges, the series diverges. What the integral test tells us is the integral and the series are of the same type. Okay, so let's look at our integral. What is our integral from 1 to infinity of 1 over x, my function of interest? The integral from 1 to infinity, 1 over x dx, is the limit as b goes to infinity of the integral from 1 to b, 1 over x dx, which is natural log absolute value of x. I don't need to worry about that as x goes from 1 to b, which is the limit. I need my limit here. Limit is b goes to infinity, which is the limit as b goes to infinity of log b minus log 1. Well, log 1 is just 0, but log b gets as big as you want it to get, so this diverges. Which means that that thing, sum of 1 over k, also diverges because they're both of the same type. So we say since the integral from 1 to infinity of 1 over x dx diverges, we know that the sum as k goes from 1 to infinity of 1 over k also diverges. By what test? By the integral test. So that's our first case, is when k equals 1. Remember, we're looking at our p series. Under our p series, sum as k goes from 1 to infinity, 1 over k to the p. How about for our next case, we say that p is greater than 1. Okay. So then what is my associated function? My associated function, f of x, is 1 over x to the p. Again, I think it's pretty clear that as you make the denominator bigger, right, the next one is going to always be smaller than the previous one. If you want to think of it that way, a sub k plus 1 is 1 over k plus 1 to the p. P is a positive number, big number. A sub k, 1 over k to the p. If the bottom is bigger, then the fraction is smaller. So a sub k plus 1 is less than a sub k. So we satisfy the condition that it's decreasing. Check. Is it continuous? Is 1 over x to the p continuous? The only time we're going to have an issue is if x is 0, and we only care about this beyond 1. So f of x is continuous on the interval from 1 to infinity, which is what I care about. And it's positive Yes, if x is positive, right, 1 over x to the p is positive, x is positive. F of x is greater than 0 on the interval from 1 to infinity. So that tells me again that the integral test holds. So the integral and the series are going to behave the same way. Again, p is greater than 1. This is our p series. Or 1 over k to the p. Sum, okay, goes from 1 to infinity. 1 over k to the p, where p is greater than 1. That's what we're talking about here. So my associated function, f of x is what? F of x is 1 over x to the p, which is the same thing as x to the negative p. And I'm going to look at the integral from 1 to infinity of f of x dx. This is the integral from 1 to infinity of x to the negative p dx, which is the limit as b goes to infinity of the integral from 1 to b of x to the negative p dx, which is the limit as b goes to infinity of x to the negative p plus 1 over negative p plus 1, evaluated as x goes from 1 to b. Now, remember, p is greater than 1. P is greater than 1. So 1 minus p, that's a negative number. 1 minus p, that is a negative number. So that fact is going to move it downstairs in a sense. This 1 over negative p plus 1 is a constant. I'm going to rewrite this as the limit as b goes to infinity. If I move it downstairs, I get 1 over x to the p minus 1, which now makes that a positive number downstairs because p is greater than 1 as x goes from 1 to b. So what do I get? I get 1 over negative p plus 1 times the limit as b goes to infinity of what? 1 over b, a very large number, to the p minus 1 to a positive number, minus 1 over 1 to some power is just 1. So what I get here is this. It's a little tricky. P minus 1 is a positive number. So a large number to a positive number is always going to get very, very large. 1 over a very, very large number is going to turn into 0. So I get negative 1 over negative p plus 1, which is the same as 1 over p minus 1. So that converges. So what we've done is we've just proven with the integral test that the sum as k goes from 1 to infinity of 1 over k to the p for p greater than 0 converges. And there's one other process that we have to talk about, and that's if p is between 0 and 1. So what's my third case? My third case to look at is 0 is less than p is less than 1, and we're looking at the sum as k goes from 1 to infinity of 1 over k to the p. So you think about p like being 1/2 or 1/3, 2/5, something like that. Now, the process is still the same. This will always be positive, and this will indeed decrease by the same argument that we had before, right? A sub k is 1 over k to the p. A sub k plus 1 is 1 over k plus 1 to the p, even if it's a square root. I mean, if the square root of 2 and the square root of 3, square root of 3 is bigger. If the bottom gets bigger, the entire fraction is smaller. So a sub k plus 1 is less than k, a sub k, so it is decreasing. Is it continuous? Is 1 over the square root of x continuous? So my f of x function is 1 over x to the p, and p is like a half, a third, whatever. As long as I'm away from 0, it is. So it's continuous on the interval from 1 to infinity. And it's positive, right? If x is positive and p is positive, it's positive. So the function is positive. So we've met all 3 conditions: decreasing, continuous, positive on the interval from 1 to infinity. So that means the integral is going to behave the same way as the series. So I look at the integral 1 to infinity of 1 over k to the p. Again, it's going to be very similar to what we just did. Limit as b goes to infinity of the integral from 1 to b of k to the negative p, except I'm sorry, I want to go with x. Let's go ahead and change those k's to x's. Because when they're x's, I see them as real numbers. When I see them as k's, I see them as integers. So the integral from 1 to infinity of 1 over x to the p dx is the limit as b goes to infinity of what? Again, x to the negative p plus 1 over negative p plus 1. Evaluated as x goes from 1 to b. So that integral is 1 over negative p plus 1. And the limit as b goes to infinity of x to the negative p plus 1, evaluated as x goes from 1 to b. Now, p is between 0 and 1. 1 minus a number less than that is going to be a positive number. This is a positive number. So now what I get is I get this. Limit as b goes to infinity of b to some positive number. Minus 1 again. But that's going to grow without bound. So this is going to diverge. Again, the key being that this is a positive number. 1 minus p in that case is positive. A large number to a positive exponent is going to go to infinity. So my conclusion then is that the sum as k goes from 1 to infinity of 1 over k to the p, if p is between 0 and 1, that is going to diverge. So let's put all this together into one giant test that we've proven 3 times with the integral test, and that is the p-series test, one of our most important ones. P-series test. The sum as k goes from 1 to infinity of 1 over k to the p converges when p is big, p is bigger than 1. It diverges when p equals 1. And that's our example that we call the harmonic series. And it diverges if p is between 0 and 1. It trivially diverges if p is less than 0, because you would prove that with the kth-term divergence theorem, not with the integral test. But that certainly would also be the case. But that doesn't typically come up. So if you look at a question like this, what is the sum as k goes from 1 to infinity of 5 over k cubed? This is not itself a p-series, but I can pull the 5 out in front. So it's 5 times the sum as k goes from 1 to infinity of 1 over k cubed. In this case, p is 3, so it converges. If this whole thing converges, 5 times a convergent is a convergent, right? A multiple of a convergent series is convergent. A scalar multiple of a convergent series is convergent. And the same thing is true for a divergent one. So we'll quickly do one of those. If instead I have the sum as k goes from 1 to infinity, 1 over, I don't know, 7 times the cube root of k. I can pull the 1/7 out in front. 1/7 times the sum as k goes from 1 to infinity, 1 over the cube root of k. which is 1/7 times the sum, as k goes from 1 to infinity, 1 over k to the 1/3. In this situation, p is 1/3, so that's 0 is less than p is less than 1. In that case, it diverges. So this gets as big as you want. This goes to infinity. 1/7 times infinity is still going to go to infinity. So my conclusion is that this diverges. So when we're using all of our comparison tests, so if we use the direct comparison test, or we use the limit comparison test, when possible, we want to compare things to p-series, because that's going to be relatively easy. So for example, you could take a look at something like this, sum of 1 over k to the 4th plus 7. You would compare this to what? This thing, a sub k, which is 1 over k to the 4th plus 7, is similar to b sub k, which is 1 over k to the 4th, which will define a p-series. This is smaller than that, and that's the sort of thing that you would use. Same thing for the limit comparison test. I'm looking at, like, I don't know, 2k plus 1 over 5 k squared plus 3k plus 9. The top is basically k, the bottom is basically k squared. My ak being all this, 2k plus 1 over 5k squared plus 3k plus 9. What do I want to compare it to? What is this behaving like? This is behaving like the top is essentially k, the bottom is essentially k squared. It's behaving like 1 over k. And we know this guy diverges, so guess what? You will see later on that this also diverges based on the limit comparison test. Here, this one is smaller than that one. This one converges. You will see later that this also converges using the direct comparison test.